Hi, everybody. Welcome back to the second half of paired samples t-tests chapter. So this is chapter 13. So let's go ahead and get back to this. We'll get to the example that we talked about last time in just a second. But before we do that, let's go ahead and take a look at where we were last time and do a couple of questions. So if you remember, we're talking about a paired samples t-test now. And t-test, paired samples t-test is d bar, that is the mean of differences minus 0 over standard deviation of d bar, which is the standard deviation of the differences divided by the square root of n, which is this stuff right here. Okay, so to start off, let's go ahead and ask a question about when we use different kinds of tests. So go ahead and answer this question right here. So for this question, this is actually A, Pearson R. Okay, now, it's not a paired samples t-test, and I'll tell you why. I want to know if your IQ predicts how much money you make. Those are two separate variables. A paired sample t-test looks at one variable in the same people two times. So for example, if I wanted to know whether or not your IQ changes after you get a job, then I would use a paired samples t-test. And what I would do is I would say, all right, I'm going to check your IQ before you go on the job market. Then I check your IQ again after you've gotten the job and you make a lot of money. That would be a paired samples t-test because I'm looking at the mean of before and the mean of after in the same people on the same variable. That's a paired samples t-test. A single sample t-test, you remember, is when you compare your sample's mean to the population's mean. An independent samples t-test, that's going to be the next chapter. It's when you have two separate groups. So if I just looked at one group who had a job, one group who didn't have a job to see what their IQs are. That would be the difference between those. So what we're going to do now is give you the definition then of the difference between a paired sample t-test and Pearson R. Now in a paired samples t-test and Pearson R, you are measuring the same person twice, but in a paired samples t-test, you compare one group of scores to another. That is, one score on the same variable compared to another score on the same variable. So both scores are from the same variable, and both come from the same person. Usually, there's actually technically some times when that doesn't happen, but it's not very common. For our class, this you should just assume that they're coming from the same person. There are instances where they could come from other people, but generally it's the same person. Pearson R, you want to see if two continuous variables correlate or predict each other. So IQ is one variable, money is the other variable, to see whether they predict each other. In a paired samples t-test, you're looking at the same variable in two times, but it's in the same person. All right, so what we need to do now is we need to go ahead and look at some data, because what we need to do is try and calculate our paired samples t-test, and then get into hypothesis testing, get into the idea of rejecting and failing to reject the null hypothesis. Okay, first things first, let's go ahead and practice calculating a paired samples t-test. So here's the data. Let's say that I have a theory. I have a hypothesis that listening to stats lectures makes you hungry. So I take each participant. I have 9 participants in this particular case. I take each participant, I measure how hungry they were before the stats lecture, that's hunger 1, and then after the stats lecture, that's hunger 2. So calculate a paired samples t-test. All right, in order to do this, we need to find the difference scores, the difference. And the difference is number 2 minus number 1 for each person. So hunger at time 2 minus hunger at time 1 for each person. So 5 minus 5 equals 0. We're going to do that for each person right here. And then I'm going to get the mean of those differences. So this is going to be the mean of all of these differences. There it is, 0.66 repeating. Then we need to get the standard deviation. We do that the same way we've always done it. So we get the deviation, which is x minus D11 is x bar. And we get each one of those. But if we add them up, that's going to end up being 0. So we got to square it. Deviation squared. We do that for each one of these. And then when we add these up, we get the sum of squares, SS. So this right here is the sum of all of these deviations squared. Okay? The variance is the sum of squares divided by n minus 1. So it's this, this 18 divided by n minus 1. N is 9, minus 1 is 8. And then we got the standard deviation, which is going to be the square root of the variance. Oh, I forgot the equals. The square root of that. 1.5. The other way you can do this on Excel is you can just go standard deviation of a sample and then put everything that you want in it. There it is, 1.5. It's the same thing. Okay, so in order for us to get paired samples t-test, we need to get d bar minus 0. This is the d bar. It's the mean of the differences. Minus 0, the same as the mean of the differences. Divided by the standard deviation, which is divided by the square root of n. So we want the square root of n, and that is, we know what that's going to be. That's going to be 3. So just to show you, we want the square root of n. N is 9. That gives us 3. So the standard deviation, so standard deviation divided by square root of n is this divided by that right there. So this is going to be our, this is what we're going to divide our mean by, okay? So that means that t is going to be this minus 0 divided by the standard deviation divided by the square root of n. And that's our t statistic, 1.3333 repeating. Okay? That's our paired samples t. Now, if this is what we got, do we reject or fail to reject the null hypothesis? Now remember, my hypothesis was that listening to stats lectures makes people hungry. So this is a representation of the difference between time 1 and time 2 in hunger. Could I have gotten that by chance? Or what's the probability of getting that by chance? Should I reject or fail to reject the null? The null is that there's no difference. Overall, there's no difference between the two groups, time 1 and time 2. There's no difference. So, do I reject or fail to reject? Well, to find this, whether or not we reject or fail to reject, we take t equals 1.333, and we need to look at a table. So here's the table from the book. Now, when we do a paired samples t-test, the degrees of freedom are n minus 1. N minus 1. The reason why is because you're actually working with a difference score. You're not actually thinking about it as two separate samples, and so it's n minus 1. Now, if you don't care, I'm always going to tell you this on an exam, but degrees of freedom for a paired samples t-test is n minus 1. So, if I had said in my hypothesis that I think it always makes you hungry and that I don't think it can ever make you less hungry, then I would be talking about this paired samples t-test, and it would be a one-tailed test. All right. If I had said I think that watching stats lectures might affect your hungry, it could go one way or the other. It could make you more hungry, could make you less hungry. That would be a two-tailed test. So what we need to look at is which way it's going and whether or not it's significant. So let's go ahead and do a two-tailed test. A two-tailed test with alpha equals 0.05. When we do a two-tailed test, alpha equals 0.05, then we are looking at alpha equals 0.05 right here, and this is the level of significance for a two-tailed test. So we're looking in this column right here. If you remember, we had 9 people. There they are. We have 9 participants here. So degrees of freedom are n minus 1. So the degrees of freedom are going to be 8. Remember, our t is 1.33. So degrees of freedom are going to be 8. So when we look at the table, degrees of freedom equals 8. And we are looking for the p-value when alpha equals 0.05. The critical value we're looking for is 2.306. 2.306. That's our critical value. We calculated a 1.33. That is not even close. So we have to fail to reject the null hypothesis. Now, does this change if it's a one-tailed test? For a one-tailed test, alpha equals 0.05. It's right here. It's 1.86. And if you remember, our calculated t is 1.33. So again, we failed to reject the null hypothesis. All right, let's try this with some data that we did last time. So let's go ahead and try it with our first example that we tried last time. And here's our first example that we tried last time. Okay? So what we're looking for then is whether or not we should reject or fail to reject the null hypothesis. Let's go ahead and do a two-tailed test with alpha equals 0.05 with this t. T equals 3.01. Now for this, remember, we're looking for the degrees of freedom. Degrees of freedom is n minus 1. N here is 10. We had 10 participants. N minus 1 is 9. So n is 10, n minus 1 is 9. That means we have 9 degrees of freedom. And our t statistic is 3.01. So let's go ahead and look at the data. All right. Degrees of freedom equals 9. Alpha equals 0.05. For a two-tailed test, we would reject the null hypothesis because our statistic that we calculated, just to remind you what that is, that's 3.01. It's right here, 3.01. That value, 3.01, is more extreme than 2.262. That's our critical value. So in this particular case, we are going to reject the null hypothesis. Now, if you remember, in that particular example, we were talking about whether or not GPA increases or decreases after we did a study program, after we had people listen to Mozart. So the question is, we rejected the null hypothesis, but which way is it going? Are people getting higher GPAs or lower GPAs after after they go through the Mozart singing? Well, one way to look at that is there's two ways to do it. One is to look at the means. So let's go ahead and look at the means. And that is the average between this group right here. So the average of your GPA, the average GPA before the Mozart studying was 2.99. The average GPA after the mode-site studying is 3.38. So when you look at it that way, you know automatically that it increased, that the mean increased over time. The other way you can look at it is, as long as you are taking the second one minus the first one, as long as you're going in that direction each time, so the difference is 3 minus 2.5 as opposed to 2.5 minus 3, as long as you're doing it that way, then if your t statistic is positive, that means that it's going to be increasing, right? That means that time 2 is greater than time 1. So in this particular case, we reject the null hypothesis and we know that the GPA is actually increased. All right, let's do one last example. So this was the other example we did last time when I changed all of the data. So I changed the data around. Here is GPA 1, GPA 2, but I changed the data around. And when we calculated t, we got a 1.23. So I want to know, does GPA increase significantly here? Okay, if these were our data about Mozart, would we reject or fail to reject the null hypothesis with a one-tailed test? One-tailed test this time. All right, for this one, we calculated our t, which is 1.23. We have 10 people in our study. So participants, we have 10 people in our study. N minus 1 is 9, so the degrees of freedom are going to be 9. When we look at our table, degrees of freedom are 9. Now, in this particular case, we want a one-tailed test. One-tailed test, alpha equals 0.05, degrees of freedom equals 9. We got a 1.833. That is going to be our critical value, 1.833. That means that our calculated statistic, our calculated t, has to be more extreme than a 1.833. When we look at ours, we got a 1.23. So we have to fail to reject the null hypothesis. We fail to reject the null. Okay, good practice. Make sure that you feel like you understand how to calculate these and also how to find whether or not you would reject or fail to reject the null hypothesis for any one of these.